So hi, I'm Nicole, and thank you for the nice welcome. So I am at Moonlight AI, and at Moonlight we use computer vision to see genomic mutations directly from liquid samples, such as a cancer patient's blood. Our goal is to create a more scalable alternative to molecular testing, and we are exploring a quantum use case in collaboration with Quantum Basel. So before I go any further, I just want to talk for a couple of seconds about how this collaboration began. This summer, Moonlight participated in the Chi Ventures Accelerator that is hosted in a quantum center of excellence located just outside of Basel, Switzerland. And this center of excellence really is bringing the entire ecosystem together to kind of create that magic of bringing quantum into a lot of existing use cases, such as what I'll present today. One of the components of this Center of Excellence is also Quantum Basel. So they are really providing a lot of the know-how as well as connecting people like me to the hardware and the solution providers. And so during the summer, I had a lot of opportunity to brainstorm with Quantum Basel because we're located on the same office floor. We did a lot of trading ideas back and forth, and probably got to go a little bit deeper in the weeds on our particular use case than you might when you have a quantum provider who's trying to get in with a large pharma company, for instance. And so I wanted to kind of peel back the curtain for you and show you how this conversation evolved and maybe start a discussion on how we can create better collaborations between AI companies and quantum companies. So the person that is my personal quantum expert on this project is Rajiv Krishna Kumar. He's been a pleasure to work with, and he's going to be implementing this use case. So at Moonlight, we noticed that despite the promise of precision medicine, patients are still struggling to get access to targeted therapies. One of the major reasons for this is that molecular testing is required for a patient to be deemed eligible or ineligible for a particular precision medicine. And yet the molecular testing is turning out not to be as rapid and scalable as it needs to serve the global cancer patient population. Just to underscore this idea with a statistic, if we look at lung cancer, which is the poster child for precision medicine, in the US, only a third of lung cancer patients are getting access to molecular testing. And some of the reasons cited for this statistic were that it's very expensive, both in terms of personnel and hardware. There are long turnaround times where you actually are delaying the patient's treatment until you find out what treatment they're eligible for. And as you can imagine, if you get away from some of the larger hospital systems, or if you leave the US or Europe, sometimes the access to this molecular testing can drop precipitously. So at Moonlight, we realized that there's room for a complement for traditional molecular testing, something that's a lot more scalable, rapid, and inexpensive. So in order to illustrate where we fit in, I want to start by showing an example clinical workflow. If you have a blood cancer patient and the hematologist treating that patient determines that they're ready for treatment, the first thing the hematologist is going to want to do is figure out what treatment the patient's eligible for. So the hematologist will take a peripheral blood sample, and part of that sample she'll send to a diagnostic laboratory for molecular testing. The diagnostic laboratory will perform a series of physical sample processing steps followed by a molecular test, for example, next-generation sequencing, and then that will be followed with a bioinformatics or data analysis pipeline. The diagnostic lab will then return the results of which mutations are present for that patient. And this part of the workflow takes anywhere from 10 days to 2 weeks, depending on what kind of molecular test that you're performing. In the meantime, the hematologist is going to do her own analysis. So she'll take another part of that peripheral blood and smear it onto a microscope slide, look at it under the microscope. And hematologists are really well trained in cell morphology, so using how a cell looks visually under a microscope to gain a lot of information about how the cancer is progressing and what the patient's specific needs are. This analysis on the bottom only takes on the order of 30 minutes. And actually what Moonlight is doing is another form, an AI-powered form of morphological analysis to determine which genomic markers are present. So what we do is we ask the hematologist to take a high-resolution image of this blood smear that they're looking at under a microscope and send it to us along with a request to detect a particular genomic mutation. We then apply a computer vision algorithm to detect very specialized morphologies that indicate that a mutation is present, and we return that information. So this entire workflow is on the order of hours, and then the patient can proceed with treatment. So what does the blood smear actually look like under the microscope? First of all, there are millions of cells in a single blood smear sample. And the peripheral blood contains quite a few different cell subtypes, each of which have very distinctive morphologies associated with them. And what is becoming increasingly known is that the presence of a genomic mutation can alter these distinctive morphologies. What we're trying to do is build a model to detect the altered morphologies. So we need to train a model that can predict the patient's mutational status by detecting rare and clinically relevant morphologies. But there's a major catch, and that is when we're assembling our training data set, it is very difficult to get access to spatially resolved single-cell genomic annotations at the scale one would need to in order to train a model that can be implemented in the lab. So what we're going to do is rely on patient-level genomic information. In other words, when we train the model, we're going to actually pair whole slide images with the patient's actual mutational status as determined by molecular testing. And in order to do that, we're going to operate under a weekly supervised learning framework. So weekly supervised learning, I'm sure some of you are familiar, but for those who aren't, it just assumes that you do not have high-quality data annotations for every single data point in your training data. And a subset of weekly supervised learning is multiple instance learning, where you actually bag instances of the data together, and you can feed a series of instances of the data to a model to ask for an overall prediction. That's essentially what we're going to do here. So we have two pieces of information at our disposal. On the left, we have a whole slide image at very high resolution from which we can extract single-cell images. At the right, from the laboratory information system, we can get the patient's actual mutational status. This is the ground truth we're training against. And so we take these cell instances and we group them into bags. And the bags need to be large enough such that the cells in the bag essentially recapitulate the overall sample. If that is attained or achieved, then what you can say is, I'm going to actually propagate the patient's mutational status down to the bag level, because the bag essentially is representative of what's going on in the patient. I don't know which cells are showing that special morphology that harbor the mutation, but I'm sure that there is at least one. And so here's a general workflow from a machine learning point of view for training the model. You have that whole slide image. You are doing segmentation to identify single cells. You're grouping the single cell instances into bags. The next step is for each cell, you're going to extract a feature vector. And at this point, you have a series of feature vectors that need to be fed to a classifier neural network to predict the overall mutational status of the patient. And that mutational status can be compared to the patient's ground truth mutational status. And what I had abstracted away is really where the opportunity for innovation is, because you can plug in a lot of different neural network architectures to accomplish this workflow. But when you do, either implicitly or explicitly, there's a problem you're going to have to solve. You're going to have to go from those cell-level feature vectors to a whole sample-level representation, a single feature vector. So you need to find a way to intelligently aggregate that cell-level information into a patient-level piece of information. And how well you do that is going to determine how the model performance that you can achieve. This is the strongest determinant of what you're going to be able to achieve in your end goal. And this is where we think there's really an opportunity for quantum computing to actually leapfrog over what we're able to do with classical machine learning. So there's a lot of research in the classical machine learning world about how to aggregate these instance-level vectors into something that represents the whole sample. As an example, the simplest version is to just take an average of all feature vectors. But as you can imagine, when we're looking for a very rare special cell morphology, the average is simply going to wash out all of our signal. There are a lot of heuristic kind of methods. There are a lot of parameterized and trainable methods. And one that's particularly interesting is borrowed from natural language processing. This is the concept of the attention mechanism, which is a trainable function that uses the content of each feature vector to learn how much attention to essentially pay to that feature vector. So for instance, it might learn that certain cell types, as defined by the content of their feature vector, are to be ignored while others are to be prioritized. Or maybe certain features, certain elements in the feature vector indicate a visual property that's meant to be highlighted, and so that will be weighted more heavily. And so the attention mechanism is the inspiration for how we formulated this essentially race between classical machine learning and quantum computing. On the left, I have our goal. So we want to learn a combining function, g of x, that allows us to combine the cell-level vectors into an appropriate slide-level representation. And just for the sake of argument, let's assume that with classical computational methods, we have, as everyone does, hardware constraints, and we have allotted ourselves a function that's trainable with 20 terms in it. That 20-term function might give us access to a relatively simple solution space, but when we take the analogy from a quantum perspective, we get 2 to the 20 terms, or over 1 million terms to play with and to learn. And this gives us access to a much more complex and flexible solution space. And we do think that this is going to be the key to being able to contextualize those subtle and rare morphologies that are so important to the performance of this model. So I'm brainstorming with Rajiv, and I'm like, okay, job done. And he says, wait a second. You have millions of cells per sample. You have thousands of elements in each feature vector. We need to scale this down if we're going to actually apply this to a quantum use case. So as I mentioned before, a bag needs to be representative of the sample in order to inherit the patient-level label. If we don't have single-cell annotations, then we actually can't shrink the bag down to a really small size and be sure that it's still representative. So what we did is we designed a toy analogy. It's still clinically relevant, and it's actually quite clinically interesting, but it's going to be an analogy where we're not detecting mutations, we're detecting cell types that are important and clinically relevant for decisioning. And the reason we're doing this is because cell types are much easier to get cell-level annotations for. So the analogy that we came up with is the detection of erythroblasts in peripheral blood. Erythroblasts are an immature form of a red blood cell that actually has a nucleus, and so I show it here surrounded by mature red blood cells that do not have nuclei. The erythroblast is usually found in the bone marrow, but when it migrates to the peripheral blood, it may indicate that the patient has cancer or a severe blood disorder. So it's really important to be able to detect these cell types. And so if you actually just take the blood MNIST data set, you get this really nice, already annotated data set of single cell images along with their cell types. So what we're doing is we are creating synthetic patient samples where we're generating bags of these different cells and we're doping in small numbers of erythroblasts. A positive bag is one that has at least one erythroblast in it, and a negative bag is one that has no erythroblasts in it. And just to illustrate how important it is to find the right combining function, I want to take a toy example of 2 different patients. At the top, you see the makeup of their blood smears, so 3 red blood cells, 2 lymphocytes, 2 leukocytes. 2 patients can have that same makeup, and the addition of a single erythroblast can completely change the clinical relevance of what you're seeing. So as you can imagine, averaging the feature vectors for each of these cells is going to wash out that signal. We need something that learns how to push the slide level feature vectors for these 2 samples far apart in that feature space. Now, moving on to what we've decided to work with from a quantum perspective. So once again, our goal is to learn a combining function, g of x, and we have a couple of mathematical conditions that we need to satisfy. The first is that we are invariant with respect to the ordering of the cells in the bag, because every bag is just a collection of cells and the sequence that we feed it to the model doesn't matter. The second condition is that we're invariant with respect to the number of cells in the bag. The sample size should not matter. So we ended up using a form that's inspired by attention mechanisms. It's simply, at the bottom, a linear combination of the feature vectors where the coefficient is actually inspired by what's inside the feature vector. So this is quite similar to what you'll see with an attention mechanism. On its own, this doesn't satisfy those two mathematical constraints, but when we use a quantum CNN or a quantum reservoir model to learn h of x, the coefficient, these give us a number between 0 and 1. And so, for instance, if you want to satisfy the invariance with respect to number of cells, you can just divide by the number of cells that you're giving, and you have your condition satisfied. So what we're doing at the moment is taking these two quantum circuits and actually putting them up against classical machine learning methods using attention networks. And this work is ongoing, but I'm excited to follow up at a later date. So I hope you found this interesting. Thank you for your attention, and I'm happy.